Okay, in our previous lesson we talked about chemical reactions and how to look for them, the signs and indicators of them. Now we're going to talk about balancing of equations. Balancing of equations is fundamental to everything that we try and do in chemistry. There's several different types of equations that we're going to have to deal with, and they all stem from the same basic ideals. The first type of equation would be a word equation. From a word equation we create what's called a skeleton equation. Now word equations and skeleton equations are good, quick, effective ways of getting the information to you, but they don't tell you everything about what you need. They don't tell you the amounts that you need. That's where a chemical equation comes in, the last type, where balancing is needed. So a word equation is simply exactly how it sounds. It contains the words of the compounds and the elements that are coming together to cause some type of reaction. A skeleton equation takes place when you take those words and you try to make them into compounds. So as we break down potassium chlorate, that's K, and that's ClO3. This is ionically bonded, -1, +1, to make KClO3. Now KClO3 is a solid at room temperature, so we also include that in parentheses afterward. Now breaks down to form means that the reaction is going to take place here. There's lots of words that can mean this arrow here, like yields or creates or makes or breaks down to form. Those are your key indicators that the arrow is happening and you're switching from reactants to products. Now we're going to form something else, potassium chloride. Well, IDE implies it's a single element anion. Chloride's -1, potassium's +1, KCl, which is also a solid at room temperature. The last thing that you're going to form is oxygen. Well, oxygen's an element, and a lot of people will be apt to put just O. However, oxygen is part of the Brinkelhoffs, which we've talked about before, and is therefore always O2. And at room temperature, oxygen is a gas, symbolized by the letter G. You'll also see the liquid, which will be symbolized with an L, and you'll also see in parentheses AQ. AQ means dissolved in water. This right here is an example of a skeleton equation. Notice we don't have anything about the amounts, we just have the materials that are present. When we're talking about a chemical equation, though, we're going to show equal amounts of each atom. Equal amounts of each atom on both sides of the arrow. And this again is completely due to the law of conservation. We can neither create nor destroy any matter. We can simply rearrange it into a different form. So some simple rules that we're going to use in order to balance. The first thing we're going to do is conduct an atom inventory. In much the same way that you would inventory a store to find out how much product you still have on your shelves, you're going to inventory the chemical reaction to figure out how much stuff you had at the beginning and how much stuff you have at the end, and how much you have to add in to make up for the loss. We're also going to only change the coefficients. From our previous video we learned that coefficients are the big multiplier numbers that go at the front, while the subscripts must never change, must always remain the same. And finally, our coefficients are going to be in our most reduced format. The third step is kind of a tip or trick that you pick up when you do these more often. If an element appears multiple times on the same side of the arrow, it's best to save it to the last. All of these reactions that we're going to be balancing actually do take place in nature. They're not all 1-to-1-to-1 ratios, and therefore they will work somehow and will work themselves out. So sometimes the most difficult things that you might have to balance will end up working themselves out in the end. So going back to the example that we saw before, we're going to go ahead and conduct our balancing rules. So we're going to conduct an atom inventory by listing out all the elements that are present. On the left side of the arrow we have 1 potassium, and on the right side we also have 1. On the left side of the arrow, our reactant side, we have 1 chlorine, and we also have 1 chlorine on the product side. We have 3 oxygens on the reactants and 2 oxygens on the products. Now, one of the key things about balancing equations is it requires you to apply some logical thinking. If I look at this here, I note that oxygen can only be found in one spot on the product side and one spot on the reactant side. So because of this, we also take note that the subscript of 3 and 2 will eventually have to equal the same number. Well, what number do both 3 and 2 go into evenly? The lowest one is the number 6. In order to get 6 total oxygen atoms on the left side, I must have the coefficient 2. Now when I put the coefficient 2 there, it changes K, Cl, and O. We now have 2 times 1 potassium, 2 times 1 chlorine, and 2 times 3 oxygen. This changes our whole plan about how to balance this. Well, we put the 2 in that spot because we wanted to get our oxygens balanced. So let's finish out that balancing. We put a 3 in this spot here to give us the 6 that we were looking for. Now that we have 6 on each side for oxygen, we can move past oxygen back to the others. Potassium and chlorine both need to be fixed, and both can be fixed by placing a 2 in that spot here. This changes both of these to 2. Now we have 2 potassium on both sides, 2 chlorine on each side, and 6 oxygens on each side. This is a balanced chemical equation. Much more practice takes place in class, but that's balancing in a nutshell.